Today, along with my teammates Nikhil and Kushi, we are here to present our project titled AVI-Cap, Attributable, Verifiable, and Interactive Caption Generation. This project focuses on building image captions that are grounded, fact-checked, and explanation-friendly. Let me begin with a brief introduction. Traditional image captioning models produce fluent sentences, but they often struggle with hallucinations, meaning they describe objects that do not actually appear in the image. Most models also lack grounding, which means they cannot justify which part of the image supports their generated caption. In addition, these models do not verify factual information about objects or entities inside the image. So to overcome these limitations, our project introduces strategies like region attribution, external verification, and interactive correction. AVI-Cap is therefore aimed at producing trustworthy image captions, useful in real-world situations like accessibility tools and autonomous systems. The main problem we address is the unreliability of existing captioning models. They describe images but do so without accountability. They cannot point to the region that supports their statement, and they frequently generate incorrect or unverified claims. In safety-critical environments, this is a serious issue. Users need captions that are not just fluent, but evidence-backed, explainable, and verifiable. Therefore, our target is to build a captioning system that grounds every important word to a specific image region and verifies uncertain claims using an external knowledge source. For this project, we used a combination of datasets. MS Coco provides high-quality captions and a large collection of everyday images. To support region-level understanding, we referred to Visual Genome, which contains object-level annotations and relationships. For generalizing to unseen objects, we considered NoCaps, an open vocabulary dataset. And finally, for factual checking, we integrated information from Wikipedia, which acts as our external knowledge base for entity verification. Together, these datasets support grounding, captioning, and verification in a unified manner. With this, I would now like to invite Nikhil to explain our proposed approach.
Thank you, Tarun. I will now walk you through the core of our project, the proposed approach for AVI-Cap. Our system is built around three main components: grounding, captioning, and verification. Let's start with the grounding module. We use advanced models like Segment Anything, or SAM, to extract precise visual regions from the image. Each region is assigned a mask, a bounding box, and a clip image embedding. Simultaneously, we extract the important noun phrases from the generated captions using natural language tools like SpaceE. We then perform a crucial step: span to region alignment. This alignment is done by calculating the cosine similarity between the text and the visual clip embeddings. This ensures every descriptive phrase is directly linked to a specific part of the image, making it traceable. Moving to the captioning module, we generate the initial caption using a vision encoder-decoder model, such as ViT-GPT-2 in our implementation. The key innovation is the post-processing step. The generated captions are post-processed to include special region tags. For example, a black dog running on the grass. This tagged structure ensures that every single noun phrase in the caption is traceable back to a unique and supporting visual region, establishing accountability for the statement. Now for the third and most critical component, the verification module. Here, every detected entity, such as Eiffel Tower or Siberian Husky, is rigorously validated against external knowledge. We perform validation through a two-step retrieval process. First, we use BM25 lexical retrieval, followed by sentence transformer re-ranking. Our source of truth for all factual checks is the Wikipedia API. This module returns key outputs: a verification confidence score, the actual supporting evidence from Wikipedia, or a clear flag indicating uncertainty about the claim. Based on this confidence score, our system employs an interactive decision policy. If the confidence is high, we assert the claim and provide a citation. If the confidence is medium, the system asks a clarifying question to the user. And crucially, if the confidence is low, the system is designed to abstain from making the claim entirely. Finally, we evaluate our system's robustness using counterfactual sensitivity. Key regions in the image are deliberately masked or blurred to see if the resulting caption changes significantly. This step ensures that the final caption truly depends on the visual evidence and is not relying on spurious or memorized patterns. In summary, AVI-Cap is designed for trustworthy, explainable, and verifiable captioning in safety-critical applications.
I will now cover our results and conclude the presentation. Our graphical visualization of results begins with two key measurements. First, the histogram of clip similarity scores shows the quality of our region span alignment. A higher similarity score indicates better grounding, confirming that our model is successfully connecting noun phrases to the correct visual regions. Second, the verifier confidence distribution measures how certain our verification module is about entity identification, which is a key metric for demonstrating the factual reliability of our system. Moving to the next set of results, we analyze the complexity of our segmentation and alignment. On average, the Segment Anything model, or SAM, extracted around 17 distinct regions per image, which shows the level of segmentation complexity the model handles. Our scatter plot of caption length versus aligned spans confirm that captions with more noun phrases produce a higher density of grounded spans, validating the attributed content. Looking at the performance metrics, we achieved an average clip similarity score of 0.45, which is strong evidence of our grounding quality. The average verifier confidence was 0.54, and we had a mean of 1.92 aligned spans per image out of an average caption length of 5.1 words. The full breakdown of our decision distribution, showing the percentage of claims we assert, ask, or abstain from, demonstrates clear model interpretability. Overall, these metrics powerfully demonstrate grounding quality, verifiability, and model interpretability. In conclusion, AVI-Cap successfully produces captions that are grounded, auditable, and verifiable. The strategic use of region tagging significantly reduces hallucinations by creating a direct link between words and visual evidence. Our external knowledge verification ensures factual correctness and transparency in the system's claims. And finally, the interactive decision behavior greatly improves reliability under uncertainty. Overall, AVI-Cap represents a significant step toward trustworthy multimodal AI, which is essential for high-risk and safety-critical applications.